Welcome everybody to the fourth webinar of 2024. We're talking about ventilation today. For those of you that might be new to our webinar series, I'm Dr. Keith Bramwell with Jamesway. I'm over the director of the consulting group and the specialist group for Jamesway. So I've talked with some of you, but I'm sure a lot of our consultants have talked with a lot of you as well. Down at the bottom during the webinar, we'll not have questions during the webinar, but at the bottom of your screen, there's a Q&A box. Feel free at any time you have questions to go ahead and put those questions, type those questions out at that time, and we'll entertain those, as many of those as we can at the end of Chad's presentation. We're all often asked if we can get if you all can get a copy of that. Yes. After the presentation, in the next day or two, you'll receive a follow-up email, have a link to this presentation with the PDF of the presentation as well. So I know a lot of people can't watch them live, but we want everybody to have the opportunity to watch them whenever they can. Also, there'll be a Spanish translation, as we've been doing the last several webinars. On the bottom, there's an interpretation box button. You can click that. It'll move you to an interpreter. Carolina, if you will explain that in Spanish, please.
Okay, thank you, Keith. Buenos días a todos, bienvenidos al webinar. Recuerden que para la opción de español tenemos nuestro botón de interpretación, es un botón en forma de globo en la parte inferior, y que las preguntas las podemos hacer en la caja de preguntas y respuestas. Adicionalmente, recuerden que al final de la presentación les enviaremos la grabación del video con la presentación.
Thank you.
Okay.
All right. So the presentation today will be given by Chad Daniels, one of our hatchery consultants. He's got a lot of experience in the industry. Spent about 20 years with Tyson Foods in their hatchery division for the corporate level, working with a lot of different hatcheries in North America. A lot on the ventilation side seems to be his specialty, although he can do about anything in a hatchery, I've come to learn. He was with Chickmaster about 12 years, and then when the Chickmaster and Jamesway merged, he's been with the combined group about 5 years, so about 17 years with Jamesway Chickmaster as a group. So a lot of experience. I have some very good information and knowledge here. So glad to have you here for our webinar, and look for you again at other ones. And with that, I'll turn the time over to Chad and let Chad share his screen and get started. If you'll leave your camera on yourself, please, so people can see your face while you talk. Thanks.
Wonderful. Good morning, everyone. Be patient with me for just a second, and we'll get this started. There we go. How does that look, Keith?
It's good.
All right, wonderful. So today for ventilation, we're going to discuss optimizing ventilation for embryo development, and then insights into consistency. And we're going to talk a little bit about the various types of hatchery systems that are out there, what's most common and what's available today in order to meet your hatchery ventilation needs. So with that, we'll get started. So we're going to cover ventilation requirements for embryo development, understanding consistency and fresh air conditions, and then, of course, talk about the types of ventilation systems. So as we've discussed many times in the past, as the illustration shows on the right, as the embryo develops, it consumes oxygen and, of course, releases carbon dioxide, and water vapor comes from that. And so oftentimes we have to remind ourselves that the quality of the hatchling will depend largely on how the embryo is able to utilize the nutrients that are provided within the egg. And so the oxygen, being such a strong requirement as a nutrient, controls how well that incubation process can go. So during incubation, we know that we have to develop an embryo with temperature, control the temperature, the humidity, turning, provide it with oxygen, which is a vital nutrient, and then, of course, the CO2 production requires us to remove that. So we're going to dive into each one of these just a little bit as a refresher. So with temperature, as our chart shows here on the right, in the beginning, it's endothermic, meaning we have to provide higher temperature in the beginning in order to start development and drive growth. Near the end, as the embryo is larger, it's at a point where it starts producing heat. So the embryo requires higher air temp in the beginning, lower in the end. So temperature becomes a function that requires control, adding heat in the beginning, removing heat in the end. When we look at humidity, external humidity affects internal moisture. So as in the illustration, as the embryo develops and becomes exothermic, this causes an increase in moisture loss from the egg. The increased internal moisture loss creates higher levels of external humidity. And meaning external, it's what we see in the machine itself as that humidity is released from the egg. Oftentimes we don't think about it quite to this depth, but when we look at an average, say an egg weight of 65 grams, a weight loss over 18 days of 11%, total loss on a per egg basis would roughly be 7.1 grams, or in a large machine, single stage machine today that will hold 126,000 eggs, that total moisture loss is 899 liters or 237 gallons. That's a lot of moisture. A lot of times we don't really put it into that kind of a perspective, but that's a lot of humidity. Next on our list as a requirement is turning. You know, it's required to keep the yolk from settling through the albumin and attaching itself to the shell wall. It also allows full development of the chorioallantois membrane. And then we know that turning in any machine is going to cause airflow in the machine to change direction. And as a byproduct of that, it improves, you know, temp control throughout the egg pack, looking for a homogeneous zone. Of course, oxygen as a vital nutrient. The consumption begins with the development of the vascular system. Consumption increases proportionally as the embryo development advances. And then as the embryo consumes O2, it produces oxygen, or I'm sorry, CO2. So we can see that in our chart here when we look at the growth day of incubation, and then we look at the oxygen consumption, and then we see the CO2 production that comes along with that. And then, of course, with CO2, as it increases proportionally, it's simply a byproduct of that oxygen consumption. So it's in a lot of cases for us with our platinum product line, we control mostly our damper openings based on CO2 because it is more proportional based on the percent or volume of fertile developing embryos that are in a machine. So at the end of the day, when we look at all of the requirements for the embryo, we know that our machines, most incubation machines today, are capable of controlling the temperature, the humidity, and the turning. But what about the oxygen? Where does that actually come from? Well, this vital nutrient is provided to the embryo by airflow through the machine that is supplied from the hatchery ventilation system. And so by definition, ventilation is the provision of fresh air into a building, a room, or a space. In our case, our building is the hatchery. The room would be an individual rooms of incubation or hatching. And then the space is the machine itself. And a different way to look at that sometimes is that our ventilation system provides the fresh air to the room. The incubation equipment consumes it from the room. And oftentimes we don't really look at it from that perspective, but that's what our incubation and equipment is doing. It's consuming the fresh air from the room. So your ventilation system should be operated to provide consistency in temperature, humidity, and fresh air volume, all while being clean and free of contaminants. So in addition to providing the vital nutrient, ventilation through the machine also provides, and this is the first piece, cooling in the form of embryonic heat absorption as it passes through the machine. So from an incubation manufacturer's perspective, we build a machine that we know is going to require ventilation because it needs that vital nutrient of oxygen. And if we're going to have to provide that vital nutrient to the machine, what else can we do with that air. And in this case, we consider it a form of cooling to the machine. It also removes that excess moisture that we talked about, the air exchange through the machine. That also helps deplete CO2 and then helps minimize airborne contaminants. So the level of hatch performance and chick poult duckling quality is directly connected to the consistency of the environment in which it is incubated. So anytime the condition of the fresh air being supplied by the ventilation system is too hot, too cold, too humid, too dry, or not the correct volume, the incubation of it, environment will be sacrificed. So in the beginning, when we look at a lot of the original ventilation systems that were applied to hatcheries, this picture illustrates just a common roof-mounted evaporative cooler. It's basically a blower that pulls fresh air across a cardboard, a wetted cardboard evaporative cooler pad. And by doing this, the air entering is slightly cooled and humidity is added to that. And then that air is basically just dumped or supplied directly into the room. As time has gone by in certain markets, rooftop air conditioning or HVAC units became applicable. And this just gave us a little better ability to discharge better temperatures into the rooms, better volumes of air, and individualized units like that. Unfortunately, along with the development of these rooftop units in the late 80s and the early 90s, we also saw advancements in controls. And in a lot of cases, it gets a little bit scary because you have this large amount of control system just to try to control a couple of units. So ventilation can get away from basics quickly and can be a little bit complicated. So hopefully we can simplify some of those things today. So when we look at a fresh air conditions in a room and trying to understand consistency, we know that we need consistent temperature and consistent humidity. And most people can understand those a little bit. Oftentimes for me, I find that most hatcheries have complications with understanding pressure. So let's discuss the pressure piece of this first. So pressure, simply by definition, is the differential between two reference points. And it's truly that simple. Unlike temperature, where we can just measure 1 point, or humidity, where we just measure with 1 point, pressure has to be the differential between two reference points. So measuring and controlling pressure differential guarantees a correct amount of fresh air in the room, supplied to the incubation equipment, exhausted into the plenum, and then to the atmosphere, as we show in this figure. So when we talk about the fact that positive room pressure guarantees a correct amount of fresh air in the room, what that refers back to is we have all the incubation equipment consuming air from this room. And as long as we're able to maintain a positive pressure, that's confirming to us that we're providing enough fresh air to meet the machine demands. And as we discussed before, with various types of incubation equipment, if this room is too cold, these machines will try to restrict how much air comes in. If it's too humid or lacks humidity, again, it's going to change the volume that it consumes. So controlling this pressure to an accurate point, that's the first key piece of making sure that we're providing enough air into the room. The second piece of this is, where's my reference point? So under normal circumstances, when we talk about rooms, we generally reference a room to an atmosphere. And so when we say a room is slightly positive, we should be saying it's positive in reference to atmosphere, or to where its reference point is. So under normal circumstances, this should be your two references for the room. When we talk about a plenum, where we're exhausting the air into, whether it be on incubators or a hatchery plenum, we're under normal circumstances, we talk about it being negative because it's negative in reference back to the room. And the primary reason we want that to be is because as long as we're positive in the room and we're negative in the plenum, we create a natural airflow that then can be consumed by the machine and then exhausted into that controlled plenum, where from there it's exhausted to the atmosphere. So from that perspective, the positive pressure control also becomes the second portion of that, which is biosecurity, trying to control various rooms that are connected in the right pressure, make sure that dirty air is exhausted to the atmosphere and not coming back into our clean incubation rooms. So if we take a quick look at some of the incubation equipment that is in use today, the classic multi-stage setter that was originally built by Chickmaster kind of comes to mind. What this machine provides an example of is a machine that has fixed speed fans internally in the machine. And when these fans come on, they create a severe negative in the fresh air intake duct above. And by doing so, it creates a natural draw of air from the room into the machine. And then from there, the machine exhausted into the plenum where it goes to the atmosphere. So in this particular case, we refer to a machine like this as a self-ventilating machine. In other words, this machine could be put up outdoors or all by itself with no difference between the supply and the exhaust. And because of the pressure created by the recirculation fans, it will naturally ventilate. So it's considered a self-ventilating machine. Again, when we look at our Jamesway multi-stage product line, even in our Platinum product line, it's similar from the same perspective. We have the fixed speed overhead fans that once they're turned on, they displace all of the air from the entrance end of the machine, and by displacing it to this portion of the machine creates a severe negative on this entrance end, and that's what it allows it to consume air from the room, fresh air from the room. And so again, it requires minimal pressure differential, and it is a self-ventilating machine. When we look at a machine that's somewhat different is with the Avita single stage paddle fan machine, which was the original Chickmaster single stage machines. In this case, the Avita single stage setter has internal paddle fans that manage air circulation through the egg pack and do not create a high static pressure differential. So it requires pressure differential from the supply to the exhaust in order to manage flow through the machine. So as you can see in this illustration, where P2 is our plenum control, it's referencing from the room to that plenum in order to manage how much airflow goes through the machine. So in this case, pressure control becomes more critical. So keys to success when managing room conditions and pressure: have a good reference point. So when we talk about reference points, an ideal situation is the outside air reference should be one reference conduit or PVC conduit that extends throughout the hatchery and has multiple outside boxes, preferably one for the roof and a couple on outside walls. Typically, that's just going to be a small plastic or a PVC box, and you'll put small holes in the bottom of this box, and then you'll fill this box with some type of like a polyester media that does not absorb moisture. And the media just helps dampen some of the bounce that you'll see with wind gusts or wind blowing. In some cases, with the roof boxes, you want to make sure you get it high enough to where it's not, the wind is not being diverted across the box because of a piece of roof mounted equipment. So it should be fairly high up on the roof. And then if it's wall mounted, like in this illustration, you should have what's referred to as a diverter plate. So if the wind comes across the ground, hits the side of the building, instead of it shooting up into the bottom of this box, it should hit this plate. And that's going to divert the wind from blowing directly into the bottom of that box. So each room controller that has room pressure control should connect to this primary PVC conduit. And so so in this illustration, when we look at a typical layout for a hatchery, we see where we have one conduit that runs through the facility with an outside reference on one end or on each end. And then in the middle, it has an outside reference up through the roof. And so each room, whether it's a washroom or a takeoff room or transfer room or hatchery rooms, chick rooms, incubator rooms, every one of those rooms have a connection then to that one conduit. So each room control then, when you look at a room and you said this is a 0.02 positive to atmosphere, and this room is a 0.015 positive to atmosphere, they both have the same reference to atmosphere. Oftentimes we see hatcheries where the reference for this room has a tube that runs out of the side of the building over here, and the setters have a tube that runs out of the front of the building over here, and the wind is coming from a certain direction. And as a byproduct, you don't have consistency in controlling pressure between those two rooms because of two different outside air references. So this is the first part of a key of having good pressure control, is having this one reference conduit throughout your facility. In addition to that, for room references, that same box design can be used, but it just needs to make sure that you locate it in the room and away from direct airflow, like say from a rooftop unit or from a supply fresh air or a recirculation fan that's mounted in the room. Just make sure the box is away from that. For plenum references, the box should be mounted away from direct exhaust from a machine. And then when we're usually see these systems installed, a lot of times we'll use 1/4-inch tubing or very small plastic tubing to connect from the controller to the reference box. Just keep in mind the tubing should be no longer than 30 feet. Anything longer should be converted to PVC. It's okay to use tubing on each end of that PVC to connect to the boxes. Just make sure that in between, if it's longer than 30 feet, you need to revert to like a 1/2 inch or a 3/4-inch PVC conduit. So maintain a positive pressure at all times. Exhaust plenums for self-ventilating machines should, such as Multistage, should only be slightly negative. Do not over-influence the machines. And then to check this, measure airflow. And in this illustration, I'm using a handheld X-Tech anemometer, and I'm actually measuring airflow from the machine. And so it's pretty simple to take a measurement under normal operating conditions, and then to set the equipment in manual so it's fixed operating, take all the pressure off the plenum by opening the doors back to the room. And now I take that measurement again. And I don't want to see that to be a change of more than 10%, meaning I don't want to over influence the machine. If my plenum is too negative, you'll have a much greater airflow when the plenum is operating normally versus when you take the pressure off of the machine. So that's just a quick check to make sure you're not over influencing self-ventilating machines. So when we look at recommendations for static pressure in rooms, we look at setter rooms generally at a 0.02 or 5 Pascal, and that's in reference to atmosphere. Exhaust plenums, you'll notice Multistage, because it's a self-ventilating machine, is just negative at the O2 or -5 Pascal. Platinum, we're just slightly more negative. The Avita has a range, and you'll notice from a 0.04 negative to a negative 0.12 in reference back to the room. And that's because the machine size can vary greatly. It can be a 30,000 egg set all the way up to 126,000 egg set. So that pressure differential has to be managed in order to accommodate the size of the machine that you have. Similar with hatcher rooms, where we see the room consistency should be slightly negative in reference back to, say, the setter room. So it's not as positive as the setter room because we want to make sure air is flowing from a setter room to a hatcher room and not the other way. But when we look at plenums, there's a big variation in hatcher plenum requirements. A part of that's because of the big variation in the type of hatcher machines that are available in the market. And in addition to that, using step programs on rooms to aid cooling the hatcher with additional airflow as you process through a step down program. And again, I'm just using that illustration to monitor airflow through those hatcher machines to make sure that I've got that plenum pressure set where it should be. The next step when we talk about pressure control is looking at it from a biosecurity standpoint. So we look at this portion of the hatchery, this being the egg room, egg receiving, egg room, incubation. That is our clean area. And then the other end of the hatchery where we have hatcher rooms, chick takeoff, chick holding, this is the dirty area. So from a biosecurity standpoint, when I look at my pressure settings, I want to make sure that I have higher pressures on the clean end of the hatchery and lower pressures on the dirty end of the hatchery. I want to make sure clean air is always flowing in this direction. This is some additional, outside of incubation areas, these are some additional recommended pressure settings for rooms, such as egg room. Transfer room should be somewhere between what our setter room and our hatcher rooms are. Takeoff room, where we pull the chicks, is the most negative room in the hatchery. And then we have chick rooms, washrooms, and clean rooms. So when we look at washrooms and clean rooms, oftentimes in this dirty end of our hatchery, we have a room where we're going to store our clean chick boxes. And that's in a dirty end of the hatchery. And the way we have to try to manage that is that the dirty chick boxes are coming into this washroom. So this is a very dirty area. And when they're cleaned, then they're stored here. So to ventilate these two spaces, similar with this clean room, washroom here for the baskets and for the trolleys, we supply fresh air into the clean rooms, and then it's pulled through the washroom, and then we exhaust that air out of the washroom. So the clean room would be more positive than the washroom, and the washroom would then be negative in reference to that. So we make sure the air always flows in this direction. So we pay to bring fresh, clean, conditioned air into the clean room where we need it, but then we exhaust it out through that washroom so we efficiently get to double use that fresh supplied air. So when we talk about trying to keep rooms consistent, I've got a couple of illustrations here. When we look at setter rooms, specifically, whether we're multi-stage or single stage, or if it's some of our older Jamesway or Chickmaster multi-stage or newer platinum product lines, in setter rooms, consistency is key, because we're consistently trying to manage the same temperature, and we're trying to be consistent with our CFM, consistent with our damper openings. When we look at hatcher rooms, we see rooms that, in reference to that, the hatcher support is the key. So in some applications, we have older style of hatcher machines that don't necessarily always manage temperature very well and create the perfect chick holding environment. So in this case, we see temperatures that oftentimes in those rooms we need to manage lower as we progress through hatch in order to support the hatcher. And we'll see an increase in CFM, and we'll see an increase in damper opening. So in the end, we're supporting the health of the chick. And so in the hatcher rooms, managing those room conditions, supporting the hatcher is the key. So here's some other, when we talk about temperature and humidity, which will be the next piece of what we'll discuss. Here's some various recommended temperature ranges for egg room, multi-stage setters, single stage setter rooms along with humidities. So as we talk about temperature, we first want to talk about types of ventilation equipment and how they work. So what's probably the most common ventilation system today throughout a lot of the world, especially here in the US market and in Latin America, and we see rooftop HVAC units. So with these, we know they have a fixed speed blower, provides constant recirculation of air, generally around 400 CFM per ton of cooling. Uses recirculated air from the room, so it returns to the unit and mixes with fresh air from the outside. So you'll see with this unit, there's a duct here that's returning from the room that mixes in the unit through air that comes in with this fresh air outside air hood. And that air is mixed and then is first cooled through the unit. And then there's also heating, and then it's provided back into the room. So with a system like this, we see it requires an excessive changes of air filters. It has a high level of maintenance. It also has a high level of sanitation, because some of the dirtiest air we have in the hatchery comes from our egg pack. And anytime we're pulling that air from the hatchery back up into units, we're going to see some excessive amounts of contaminants and debris that gets built up into these units. So when you take a look in a typical room, you would see where the ducting is here in the picture, and the supply air simply comes out of the discharge grill, and the return air comes back up through a filter rack and is pulled back up into the unit. So when we look at a system like this, an HVAC unit, typically they only have a couple of stages of cooling and a couple of stages of heating. And as a byproduct of that, you'll notice that these units have the capability of having a large discharge air temp variation. At times will be as low as 60 and maybe as high as 120 degrees. And that discharge air then coming into the room can be very inconsistent. And that's what gets consumed by the incubation equipment and causes that inconsistent environment in the incubation. So when we look at units like this, I get asked a lot of questions about, what do I see when I look at this room? One of the first things I notice is I see that there is a vertical wall built at the front of the machine. And so what that does is it confines our space that we're trying to ventilate to directly right here in the front of the machine. And as an illustration or as a simple exercise, what I see when I see this is I see an issue possibly with having a really low or a short air exchange rate. And so to understand that, we use this as an example, but we look at a room that is 50 feet in length, it's 15 feet wide, and it's 18 feet tall. So when I multiply those, I have a total of 13,500 cubic feet of air in that room. And because I have 8 incubators in there consuming a large volume of air, I have a 16-ton HVAC unit on the roof that's moving 6,400 CFM. So with quick math, it tells me the air exchange in that room is 2.11 minute air exchange. So what that means is every 2.1 minutes, all the air in that room has either gone through the incubation equipment or has been pulled back up through the rooftop HVAC unit to be reconditioned. And so we can see a unit on the roof that has to cool, or a heat cycle has to function, and it can quickly change the room temperature. So in a room with a 2-minute air exchange like this, you may naturally create a temperature variance in the room as much as 8 or 10 degrees and you can't control it. It's because we've confined the space too much, and the rooftop unit isn't designed to fit this particular type of application. In some cases, hatcheries want to build a drop ceiling across here. Well, this 2-minute air exchange may end up as a 1 minute and 20-second air exchange. So your problem just gets worse. So we do the quick math on this. It tells us our outside air damper is going to function around 34% when we're feeding the 270 CFM per incubator. So some advancements that have been made with rooftop HVAC units, and I'm not trying to tell you to go buy this system brand new to put on a hatchery, but if you do have existing units and you have to replace them, you need to consider some of these new options. One being a variable load refrigeration compressors. That allows you to have some variable control of the discharge air temperature when the HVAC unit is cooling. That'll help avoid some of those big swings in temperature. In addition, natural gas heat can also be purchased with modulating. So again, trying to control that discharge air. And then dehumidification has been available on these rooftop units for a while. And really just in the past few years, seeing more customers actually requesting this. So in a lot of our applications, controlling the room temp is one aspect of it, but keeping the humidity from being too high is also, a little bit of a luxury, especially with a dehumidification on a system like this. But it's very critical and very important in the summer to aid with moisture loss during incubation. So the next type of system that we see that it has really today is probably the most popular system is what's referred to as an Airway modular system. And as you see in the picture, you'll have multiple units. And in this particular case, they're setting on the ground beside the hatchery. This is a fresh air intake end of the unit. And then it has a discharge duct that will go into an individual room or to a specific task. So in this case, individual units are specific for the certain areas, and they utilize a variable speed blower to provide the rooms with the non-recirculated 100% fresh air. And so typically with this unit, I'm going to have one set of filters here, but because I'm not recirculating any air from the room, the unit itself and the ducting feeding into the building will stay very clean, and they're a very sanitary system. So it requires a minimal amount of air filters. Heating and modulating cooling provides precise control of temperature of the air being supplied to each room. So it's really the key of giving you consistency. So a system can include any number of modules. And when we see a little bit of a different illustration here, it's where it has supporting chiller, the tanks such as the cold water, the warmed water returned from the incubation equipment, hot water modules, pump modules. All of these become modules that support these air handling units and the incubation equipment. And in addition to that, heat recovery is applicable with a system like this. So I can use that warmed return water from the incubation to preheat all of the outside air coming in to save on heating requirements for the facility. In addition, that warmed water can also be used to reheat air when you're functioning as a dehumidification mode. So the energy efficiency is very applicable with heat recovery on these systems. When we look at how these systems are ducted, these units set, again, these illustrations show them on the ground. Oftentimes a hatchery built new, these units will be setting in the USA or the attic space above, say, an egg room or above the incubation areas. So it is accessible from inside the building up in the attic space versus on the ground outside. So there's a lot of flexibility with these systems and where these units, get installed. So in this case, we have two. We've got one unit that's supplying pressure control to this duct, and then each room is individually controlled with a modulating damper. So we're only supplying the amount of air into that very small space that is required by the incubation equipment. And we see the same thing when we look at processing areas such as transfer rooms and chick takeoff areas. So the next type of ventilation systems that are in the market today that we see is referred to as a CC3. It's a climate control with 3 solutions. Essentially, it's providing all the ventilation into the hatchery. It also has all of the tanks that are built into the unit. The controls are built into the end of it. It has heating and cooling built in, and it has the ability to do heat recovery and dehumidification. So essentially, it's the modular system. It's just all built into one unit. And so a lot of times hatchery applications will utilize 2 or 3 of these airway systems for just one hatchery, depending on the size of the facility. And again, the ducting on a unit like this is a little bit similar to the modular, but you only have one supply. So in this case, the discharge air temperature is controlled specific to generally incubation rooms, but then where that supply duct goes on to hatcher rooms, you'll see a supplemental heating cooling coil that'll be in this duct here. Same for chick rooms, where those rooms could be controlled to a lower temperature to satisfy the needs for those rooms. So when we look at both of those types of systems, the Airway Modular and the CC3, we recognize that because we're controlling the temperature of the air being discharged into the room, now the room can be, you can have that drop ceiling, you can have a very small space, and because that temperature variation is gone, you're controlling the temperature in this environment very precisely in order to meet the needs of the incubation equipment. So it makes for a very clean installation, and it's very easy to control. So a well-designed ventilation system provides complete support for incubation, process, and biosecurity. That system should provide oxygen for incubation, deplete CO2 during incubation, help remove heat from embryonic development, moisture removal because of the amount of moisture that's comes from the eggs, during incubation. And then it should provide you the ideal condition for setters and hatchers to support the incubation. And then, of course, biosecurity. And so with that, I think that's everything I wanted to cover today, Keith. And so at this point, if anybody has any questions, I want to say thank you for having me today. And as you can see, we covered a lot of a wide array of information with this. So any questions you have, I'm more than happy to hopefully try to answer those.
Quick question. When you could go out and visit your hatcheries and say they just bring you in for a general assessment, how often is there opportunities for improvement in the ventilation? I see it quite a bit, but in your experience, is it a pretty critical thing as far as what people are neglecting?
So in the case of, let's say, older facilities,
you can unshare your screen now. Sorry, Chad.
Oh, okay. Yeah. So in the case of older facilities that are generally multi-stage, both Chickmaster and Jamesway both, it's probably 95% of the time there are opportunities in those facilities for one reason or another. A lot of times it's the equipment wasn't designed the way it should have been, or it's not controlled the way it should be, or it's not maintained adequately. And then, oftentimes we even go into newer facilities that have modular or have central type ventilation systems. In a lot of cases, those run pretty well, but it's small pieces of things that it's maybe a misunderstanding of how to run the system. And they have maybe odd pressure settings, or they're trying to over influence machines. So when you look at it from that perspective, almost every time you go in a hatchery, there's ventilation that needs to be addressed in either one area or another, almost every time.
What would be some signs that you would see that would indicate, hey, we might have some ventilation issues? If you're just going in, they're not throwing that out there, you're just looking at what's going on in the hatchery. What are some good signs you would look at?
So we see a lot of temp variations in the machines because we're not providing the incubation equipment with consistency and temperature. Also, we deal with seasonal adjustments where we have way too much moisture loss in the winter because of dry climate, or not near enough moisture loss in the summer because of lack of dehumidification and way too much humidity. And then oftentimes a lack of airflow through the machine itself causes that lack of moisture loss and causes overheating and heat stress in the embryo. And so we have losses of hatch, and we suffer from a chick quality perspective because of creating that poor environment for incubation.
So if you're looking at just chicks, would you say you're going to have, if your ventilation is not good, you're going to see reduced hatch or bigger hatch window or poor chick quality, or what of those things is jump out more likely?
Yeah, so from that perspective, you do see not a well-defined hatch window. You see chicks that are chick yield is not in line with where it should be. Of course, moisture loss measurements are not going to be correct. And then, in the chick itself, you see a lot of bigger bellied chicks, poor navel conditions, hawk issues because of not being able to pip and correctly. And then you have a lot of hatch loss with lack of moisture loss because there's just not a big enough hair cell for the chick to, basically progress into as it internally pips, and then to be able to externally pip successfully. And so it's a combination of everything. And instead of being, maybe off as much as 3 and 4% on hatch of fertile as a byproduct of poor ventilation, and then you see the increases in 7-day mortality, and it can come from biosecurity issues, heavier contamination, more bacteria loading, things of that nature.
Yeah. A lot of it can contribute to a lot of different things. Back to the hosing, you referenced having that hose run out if it's longer than 30 feet, you need to do a PVC. What are some things that you might see if somebody's got a long connection to their outside air reference, but they have used hose instead of PVC? It's a long connection. What would you see?
Well, and that's a great question because that's a very common thing we do see is hatcheries that use 100 feet of tubing from a individual room controller to an outside or to a room reference. And with that tube length like that, when it gets over the 30 feet, what it does is it dampens it. It restricts that air. So the sensor itself, what's measuring that differential, can't see it very quickly. And as a byproduct of that, you just never consistently have good pressure control because it's always reading it's giving you the wrong reading. A lot of times you'll see a plenum, for instance, a hatcher exhaust plenum, where you can stand and watch the control and the plenum pressure is going up while the fan is speeding up. And then by the time that long length of tubing lets the sensor see that the plenum is severely negative, the fan is running too fast. So now the fan tries to slow down, and it just creates a, kind of a seesaw effect where they're never in cycle with each other. So fans are ramping up and down constantly.
So there's a lot of fighting going on.
Oh, and the airflow through a hatchery. I was in a hatchery just the other day, and that exact thing was going on, and standing there measuring airflow through a hatcher and monitoring CO2 as well. And for a period of a minute and a half, there was virtually no airflow through the hatchery at all. And then it would ramp the other way and would end up at as high as like 18 to 20 CFM per 1,000 chick going through that hatcher. So the hatchery, the environment in the hatchery was just horrible. I mean, temperature was all over the place.
Okay. In terms of your positive and negative pressure and stuff, if you fail to have the right positive and negative pressure throughout the hatchery, not talking about the machines specifically, but the hatchery itself, can that have a negative effect on our biosecurity if we don't have that running properly? And how would it affect it?
Yeah, of course. So when you're in that situation where and we oftentimes see that where pool rooms, say, and clean rooms are not balanced correctly and airflow and pressures are not right, we end up with really dirty hatcher baskets, even though the tray wash may be at the right temperature and they come out of there clean, then we're loading them with a lot of dirty chick down from the pool room, and we're reloading baskets back with the bacteria again. And then we start seeing chicks in our hatch that are picking up this bacteria, and it can be as simple as that. That's all we've done is we've things that should be clean that come in contact with a hatching chick then is carrying this bacteria load, and they're wet baskets, and so it creates a perfect environment for bacteria growth to occur.
Yeah, we're just kind of taking dirty things, let it seep back into our clean area, and it's never good. In terms of the plenums, one, can you explain a little bit more of the role of our air plenums, and then what kind of pressures we're looking at? I know you talked about, well, what's really the role of the plenums?
So in the early days of commercial incubation, where we started seeing machines that were bigger and larger egg set capacities, in the name of building facilities that could hatch larger volumes of eggs and build those at a lower cost. Back in those times, in early on, and really it was this way up and through into the early 90s, we didn't have plenums on anything because we couldn't pressure control them. The technology wasn't there to allow us to actually pressure control an area. And so it was common back then to have machines that exhausted back into the room or didn't have these plenums at all. And we just didn't have the ability to manage, the airflow. So airborne contaminants and then dust contaminants out of hatching equipment, all of that air was just dumped back into the room. And so we constantly fought the bacteria back then. And we wonder why we used things such as potassium permanganate and tons of volumes of formalin in our hatching processes. And we fogged incubator rooms constantly. And it was just all in the name of trying to battle the bacteria. So when the pressure controlled plenum, when we finally had that technology and was able to do that, encapsulating all of the exhaust air out of the incubators and to the hatchers, and then exhausting that to the atmosphere, allowed a complete control of that bacteria and getting it out of the process and giving us fresh, clean, supplied air to the incubation equipment. And so it allowed us to back off of how much chemicals we were using for fogging and sanitizing and formalin and things of that nature. And so the plenum played a really key important role in managing airflow through the machine and encapsulating those contaminants and getting it out of the facility.
In terms of your incoming air and air filters, is there any type of filters to avoid or stay away from? I mean, when we're trying to ventilate a hatchery?
Well, the one filter that you should never use in any hatchery in the world is a washable, reusable filter. Just to be open about it, we don't manage those correctly. The normal process is that those filters should be cleaned and sanitized with really hot water and then allowed to air dry in an outside environment. And then you have to apply a treatment or a coating to them or they won't collect dirt. And so those types of filters don't really do anything but knock down June bugs, basically. And so that allows all of those airborne contaminants and dust and dirt and debris to simply get back into your ventilation system. So it's a no-no to use those. A lot of the current available cardboard pleated type filter medias aren't really designed for hatchery applications because the cardboard gets damp and then it collapses. They have a tendency to face load. And so what I generally recommend for most applications in hatcheries, especially in return air type systems, is generally like a 2-ply or a 3-ply polyester media. It's it's referred to as a link filter. It can be, you can buy that today and it's got a antimicrobial applicant on it. So it keeps bacteria and mold and anything from actually growing in the filter itself. Those have a tendency to depth load. I see a lot of hatcheries today where they're buying that particular type of media in a large roll, and they're simply mounting the roll on a wall. Looks like a giant toilet paper holder, and they'll just pull off what they need and measure it, and they'll cut it, and then they go place that on the return filter rack. And so it's economical. You pull it off and throw it away with each hatch cycle, and people will do a much better job of changing those types of filters than they will if they're using a cardboard or a washable type filter. So the polyester media, a link filter or rolled media that's multiple layers in depth of thickness, have a tendency to do a much better job, and thank goodness we are seeing that gain popularity.
Yep. You mentioned in your talk that you know, the multi-stage, they're self-ventilating to an extent. So if somebody has a multi-stage, would you recommend trying to power ventilate, or is it okay running the way some of them are? Do you see any advantages to it?
Well, the advantage comes in the fact that you're still going to encapsulate all the discharge air from the unit or from the incubators and take that to the atmosphere. So you avoid the heat and the moisture that comes out of the incubators and any airborne contaminants. The key to it is just to not over influence the machine. You know, at the end of the day, you're only required a specific volume of air in order to maintain the oxygen as a vital nutrient to the developing embryo. And anytime we try to over influence that with excessive volumes of air, then we're going to see incubation equipment that struggles to maintain that environment. And so under normal circumstances, as long as we don't over influence it one way or the other, either by restricting air or over, forcing the machine to consume too much air, as long as we stay in the middle of the road with that, it's the best of both worlds. The plenum is the best way to go and help us manage that.
Okay, well, a few more questions here. When somebody's got different zones in their incubator machine, what are some of the points you would be looking at if we're trying to look at a uniformity of ventilation through between the zones in the machine?
Yeah, so air distribution entering the machine, like in the older Chickmaster Classic.
How would they measure? What can they look at? Is there something that jumps right out at them, or do they need to actually go in and start measuring intake in different places?
Well, the key to it is monitoring the machine operation. So if I see a machine that's balanced, I see consistent and even volumes of heating and cooling that occur between those zones. And if I've got if zone 1 is cooling a lot and zone 2 is having to heat a bunch, that means I have a poor air distribution balance. And so that's my number one indicator right there.
And the other thing too is if you start getting a very ununiform hatch.
Oh, exactly.
Like window's really huge and uniform's like what's going on in our incubator cabinet. So that's where we might go and investigate what's happening in different zones or something. Right?
Yeah, that may be your very first indicator. As you see chicks that are coming off really early, you've got a lot of pippers at an excessive volume of pipping occurring at a 19-day transfer and out of one spot of your incubator, but then you have a lot of late, pippers or a lot of live pips in your residue, at pool that came out of the other zone. And that's generally the first thing we see. That's by far the first thing. Somebody says, hey, I've got a spread and hatch, and I've got chicks that are dehydrated and they've been out for 48 hours, and I've got other chicks that don't have enough time to get out, and that's telling us we got a temp variation in incubation.
Yep.
Yeah.
Yeah. With single stage incubation, one of the people here is asking about the where we don't ventilate, we keep our dampers shut for the first 8, 9, 10 days during incubation. What are your thoughts on that? And as far as what benefit we get out of that? There's a couple of benefits, I think. I want your opinion on that.
Well, I was with Tyson Foods when single stage was first being introduced in the U.S. market as applicable to broiler hatchery operation. Prior to that, single stage incubators were just really small, and you couldn't afford to build a hatchery with 250 incubators because they're so small. So once the incubation manufacturer started commercially building them large enough to fit that application, some of the first discussions around it was, well, we're exposing that embryo to high levels of CO2 in the early incubation process, and as a byproduct of lack of oxygen, you're going to have a larger vascular system development. You're going to have larger organ growth that comes from that vascular system. And while those points are true, but we haven't necessarily completely 100% made determinations of how much that actually changes the health of the bird through its growth cycle. What we do know is when we're not introducing fresh air into the machine in the early stages of incubation with a closed damper in a sealed environment, we're allowing the egg pack itself to be as homogeneous as possible. Consistency from one egg to another throughout the machine as far as temp control, and not seeing temp variations occur in the machine. And we feel really at the end of the day, that's probably by far the most critical piece of improved hatchability and chick quality that comes out of single stage, is that first 6-7 days of just very, very stable temperature environment and humidity environment and controlled environment. So we've eliminated the variations that we see anytime we deal with multi-stage. We've got a couple of days a week we're setting eggs, a couple of days a week we're transferring, a couple of days a week that we go in and we clean up. So there's 6 cycles that occur in those machines in a given week. And so any egg incubated through that 18 or a 19-day duration has probably been exposed to maybe 14 or 15 different variations of a temp cycle where there's just too much inconsistency. And so with single stage, we eliminate that. We create the consistency throughout.
They said they still use old swamp coolers in a few of their rooms. And then they have to winterize them in the cold weather. What are your recommendations during those cold months for ventilation if you've got to cover those up? Besides
it's always a challenge, especially in, say, chick pool rooms and clean rooms where, hatcheries that have a pool room with a small Resner heater, a clean room with a small rooftop Resner heater, or maybe it's a small Aeon heater, but then they have all these evap coolers and wall exhaust fans that operate during the heat of the summer. And so you have all this air exchange rate when that equipment is working, but then when you have to turn it off during the winter, all of a sudden you have rooms that are full of chick down. You have tons of steam that's in the air, and really you're going for that several months of the year in the U.S. market where those rooms just don't ventilate and pressure control the way they should. And so we see bacteria challenges become much greater during those times of years. And so what some hatcheries have tried to do to alleviate that issue, obviously upgrading the ventilation in those areas is the proper step, but the small piece around that is trying to take maybe 1 or 2 of those evap coolers, and while you'll shut the water off to them, you'll remove the cool cell pads, let the blower run to create their exchange. Even though that air is going to be very cold, you've got to direct it in a place into the room where it doesn't doesn't affect the people, and it doesn't blow directly on, the chicks while they're being staged up to a separator. But the other piece of that is you've got to have a variable speed pressure controlled exhaust fan then. So it'll run while those evaps are open, and running, and that it lets you control the pressure. It's not an ideal situation because the air coming in may be extremely cold at times, but it's the best thing to do between that step of not having good ventilation and in the process of maybe replacing it. And that's about the only step you can do, is try to add a big variable speed fan and still let a couple of one or two of those evaps run. It just simply in the name of trying to manage air exchange rate and control pressure. Get rid of the steam, get rid of the chick down, and still have good control of not dumping, all that contaminant back through the rest of your hatchery.
What if somebody has high pressure in their hatchers? What the effect on hatchability or chick quality would you likely see? Essentially, it messes up your ventilation, so you're not having uniform ventilation if you've got too high pressure. There's a number of things that could happen, but what might you see?
Yeah, so if I can't manage airflow through that hatcher at all times, then, with a lack of ventilation, you're going to have mold issues. You're going to have buildup of contaminants, lack of oxygen, possibly even heat stress on the chicks. And then, the other side of high pressure oftentimes goes the other way. It's just way too much airflow through the hatcher. And we create a situation where, once that chick externally pips, he's only got so much liquid on his body, and they only have a certain amount of time to get out of the shell before they maybe get too dry and get stuck in the shell. And so if we put way too much air through a hatcher, commonly we see that as a byproduct. Mm-hmm. And so we lose some chicks that get stuck in the shell, and then we also see a really, really dry residue, shell membranes that are very brittle and dry, and then it's just easier to dehydrate the chick. So they lose that much more moisture before we ever get them pulled. So.
Yeah. Yeah, it's not one of those situations where the more the better. Like if you have too little ventilation, that's not good. But if you got too much air movement over eggs, that's usually not good either.
Right.
If the air's passing too fast over the eggs, it doesn't really pull the heat out as you want to. One last question. We've got a few here. So if we haven't gotten to your question yet, it might be a little bit detailed. We need to answer it by email. But just a discussion on, during the incubation period, how much oxygen is typically required at the initiation of incubation? And then at the time of hatch, you've got CO2 rising, and what effect is on the eggs at that time?
Yeah, so, with single stage, when we talk about it, the things we learned from single stage incubation kind of makes the ventilation people go back and look at multi and rethink about how we ventilate multi. But, when you look at single stage in the early days of when we begin to open the damper, and that may vary between 7 to 9, 10 days, but in the very early portion of that, you're looking at volumes as low as a half CFM on a per thousand egg set basis. And then that may be a number as high as a 3.2 to a 3.5 CFM per thousand just prior to transfer. And with that volume of CFM going through the machine, we're able to maintain CO2 at an adequate level, telling us we are ventilating enough to deplete the CO2, and therefore we know we're providing enough oxygen to the developing embryo. But then once you get into a hatcher machine, you're starting off very close to that 3.5 to 4 CFM per thousand. But as soon as that chick begins, internally pips and then externally pips, that number escalates pretty quickly. So you end up from a 4 or 5 CFM per thousand up to more like a 9 to 10 CFM per thousand. And then we see numbers greater than that with old hatcher machines that aren't capable of cooling very well. So it uses the air to kind of help cool the chick as well. And in those, you'll see as high numbers as 15 CFM per thousand. But really, it's not needed more than about 8 in order to maintain oxygen and deplete CO2.
And at the time of hatching, that CO2 is kind of gives the chick a little kick. I mean, if you think about it, when it pips into that air cell, that first air is higher CO2, and it kind of gets it to accelerate. We've got to get out of here. We got to get out of here type of thing. So in the incubators, it's kind of this balance. There needs to be some CO2, but not too much, obviously. But we
Right.
can't just have all oxygen, nothing, because that seems to help them. And that's kind of the idea with the hatch sense that we have, is it helps manage that to kind of encourage them to hatch out more uniformly. So.
Well, the question I get asked commonly historically, when we look at, say, our 2 product lines, Chickmaster was never really a big proponent of pushing, say, CO2 damper management as opposed to humidity control. Yet with our Jamesway Platinum line, historically, most customers use the CO2 to control the damper. And the way I've always looked at it, and it kind of boils down to this, in the world where we're able to always manage the incubation room temperature, humidity especially, and be consistent with those, we can manage a damper strictly by CO2 and be more successful. But what that's doing for us at the end of the day, it's giving us an ultimate control over energy usage, because we're really only ventilating the machine with the amount of air needed to feed the volume of developing embryos that are in the machine. If we overventilate from that, we're just bringing in outside air in the name of basically trying to cool the rest of the world, because we're heating it, we're cooling it, we're dehumidifying, we're adding humidity, we're consuming all that energy, and we're just dumping it through the machines, and we're not really controlling that. So if we can manage the environment correctly, it helps you minimize how much energy consumption you have based on the volume of air that has to come into the facility. Unfortunately for us, what's common is that we don't have the ability to dehumidify. And so we have to kind of start pushing the limit a little bit on how much air we want through the machine, in the name of just trying to get to your adequate level of moisture loss.
Yeah.
In the summer and high humidity, we've seen that with our Platinum line, where we have customers that still run on CO2, but they'll lower their CO2 settings in their profile in the name of getting enough air through the machine to meet adequate moisture loss levels, because the room is way too high in humidity.
Yeah, and when we don't, in those first stages of incubation, if that damper's not opening and closing a lot easier, it's a lot easier for that machine to maintain the environment it wants and the eggs need, because it's not bringing in different air all the time to a point. But one last question real quick, and then we'll let everybody go. So how does somebody go about measuring their air pressure in their machines?
Yeah, so for me, I use and anymore when I travel, even if I'm just going somewhere to look at just strictly some incubation equipment, you'll notice me always, I'll carry a handheld anemometer, the one I showed in the illustrations earlier, to measure airflow. But then in addition to that, I'll always have a manometer, a Dwyer manometer, which is just a digital pressure measuring device. And of course, it has 2 ports on it. So I can easily go into any machine and start measuring pressure across the machine, whether it's across the fan boards or whether it's between the entrance end of a Jamesway multistage back to the room, or from the entrance to the exit, or from the exit to the atmosphere. And it lets you measure those pressures with that handheld manometer. And it's just a Dwyer manometer that I carry with me. It's pretty small. Sometimes the airport security will flag you because it looks like a taser, but it's not.
Take it out and try and tase it, and they see it doesn't work.
They take it out and look at it, and then one guy wanted to blow, and I was like, don't do that. You'll damage it, and then you'll have to pay to have it repaired. But they quickly realize it's not a taser, but it does look like a taser.
All right. Well, thank you, Chad. That was a very good presentation. Had a lot of good information and quite a few questions still that we weren't able to answer here, but we will answer them directly through email and shortly. So again, thank you everybody for joining us today, and thank you, Chad, for your remarks, and Carolina and everybody behind the scenes, their translation, everything. So I hope you all have a good day.
Thank you. Everybody, have a good day.